Hey Monty, what are you doing?
This is interesting, Kuya. My teacher gave us an MP3 file of what she said is the sound of the sine function. Can you imagine that? A function that has a sound. That's cool. It is understandable to hear sound from your guitar or any instrument, but to hear a trigonometric function is really something, isn't it, Kuya?
You're right, Monty, but I think I know the main idea behind it. Let me have the other earphone so we can both hear the sound.
Okay, let's do it.
Alright. You know, Monty, sound is a form of energy, just like electricity or heat. It's made when air molecules vibrate and move in a pattern called waves or sound waves.
Are you saying that sound is just like a wave?
You're right. Can you now deduce how it's possible to hear the sound of the sine function?
I think I know now. This must be related to graph of the sine function.
Here's the graph of the sine function. Can you explain how Monty relates this to the sound we all heard?
As we can observe from the graph of the sine function, we see a wave that starts at 0, goes up to 1 at pi over 2, then comes back to 0 at pi. It goes to negative 1 at 3 pi over 2, and finally climbs back to 0 at 2 pi.
We know that the same sine function has period 2 pi, and this means that the basic wave shape repeats endlessly to form the full graph.
And what do we call this basic shape?
It is called the sine wave.
Very good, Leah. This sine wave is the one we have just heard.
And we can hear the sine wave because sound is basically a wave. What about the cosine function, man?
Class, the graph of the cosine function y is equal to cosine x can also be viewed as a sine wave. Here's its graph and let's analyze why this is so.
It looks exactly the same as the graph of the sine function, except that the horizontal shift must have occurred here.
Can you explain what you mean by this horizontal shift?
What I really mean here is that the graph of the cosine function can be obtained from the graph of the sine function by simply allowing a horizontal movement of the sine wave pi over 2 units to the left.
Can you now describe the wave of the cosine function starting at x equals 0 up to 2 pi j?
Yes, ma'am. At 0, the function has value equal to 1. Then it goes down to the value of 0 at pi over 2. This descent continues until pi, where the value of the function is equal to negative 1, and eventually goes up again. Back to the value of 0 at 3 pi over 2, and eventually at 2 pi, where the value of the function becomes 1 again.
I think the behavior of cosine function in relation to the sine function can be explained by the equation cosine x equals sine of pi over 2 minus x.
You are right about that, Joseph.
I think that the cosine function has period 2 pi too.
Very good, Leah. Since the period of both the sine and the cosine function is 2 pi, we shall also call this number the wavelength of the sine wave. This is basically the distance between two successive peaks of the sine wave.
There is also one characteristic that the sine wave has that I'd like to mention. I have observed that the maximum distance of the graph from the horizontal axis or the x-axis is 1. Isn't this the amplitude of the new wave?
Yes, Doms. Class, we have seen the graphs of the sine and cosine functions as sine waves with wavelength 2 pi and amplitude 1. Let us now study graphs of other functions that are variants of the equations y is equal to sine x and y is equal to cosine x. Alright, let us consider first the graph of the sine function. In order to graph the first equation, let us plot some points that will correspond to the following ordered pairs.
Wow! It seems that the graph of the sine function y is equal to sine x has moved to the right by an amount of pi over 4, isn't it?
I think you are right, Doms. The graph of the sine function was shifted horizontally to the right by an amount of pi over 4.
The two of you are right. Let us now move on to the next equation. Again, we let the graph of the sine function y is equal to sine x remain in our coordinate axis, and then plot some points on the graph of the function y is equal to sine x plus pi over 4.
I think I know now.
Would you like to elaborate on that?
This time, we see that in order to graph the equation y is equal to sine x plus pi over 4, we only have to shift the graph of the sine function y is equal to sine x to the left by an amount of pi over 4 units.
You are certainly right, Leah. Equations of the form y is equal to sine x minus a can be graphed by merely shifting the graph of the sine function horizontally by an amount equal to the absolute value of a. The shifting is done to the right if a is greater than 0 and to the left if a is less than 0.
What about the equations of the form y is equal to cosine of x minus a?
Good question, Dogs. The same rule can be applied to such equations too. Let us discuss these problems one at a time. Who would like to do item A?
May I try it, ma'am?
Okay, Doms, explain your work then.
I would like to start with the graph of the cosine function. Just as we have discussed a while ago, the graph of y is equal to cosine x minus 2 pi over 3 can easily be drawn if we'll do horizontal shifting on the graph of the cosine function y is equal to cosine x. Since y is equal to cosine x minus 2 pi over 3, as the form y is equal to cosine x minus a, where a is equal to 2 pi over 3, which is positive, we then move the graph of the cosine function to the right by an amount equal to absolute value of a. It is equal to absolute value of 2 pi over 3, which is also equal to 2 pi over 3. This shifting yields the graph of the equation y is equal to cosine of x minus 2 pi over 3.
Very good, Doms. What about the second equation? Any volunteer?
I'd like to do it, Miss Crystal.
Go ahead, Leah.
We apply the technique Doms used. Let us start with the graph of the cosine function y equals cosine x. Since the given equation y equals cosine of x plus 2 pi over 3 is also of the form y equals cosine of x minus a, where a is equal to the negative of 2 pi over 3, then we do horizontal shifting to the left by an amount equal to the absolute value of a equals to the absolute value of negative 2 pi over 3 equals 2 pi over 3. This will then give the graph of the equation y equals cosine of x plus 2 pi over 3.
Very good, Leah. Would you like to summarize what you have observed from these examples?
Okay means sketching the graph of the equations of the form y equals cosine of x minus a requires horizontal shifting of the graph of the cosine function this time. Again, the shifting is done to the right if a is greater than 0 and to the left if a is less than 0.